Hi students, welcome to lecture 71 in our course, and today I'm going to talk about the Tresca and von Mises failure criteria. Now when you learn about these failure criteria, you will realize why we have been putting so much importance on finding the principal stresses of a given stress state. So these failure criteria will use these principal stresses to tell us whether a material has failed at a certain point or not. I'm Dr. Ranjan Ganguly. Now let's just look back at the aircraft picture and look at a point on the wing. We now know that at this point on the wing there is a stress state which can be given by the stress matrix. Also we can write it in a more compact form as a stress vector, and there are three normal stresses and three shear stresses. If we find the eigenvalues of this stress matrix here, we are going to get three eigenvalues, and these are going to be sigma 1, sigma 2 and sigma 3, and we can write this matrix in this form also, that is sigma is a diagonal matrix with sigma 1, sigma 2, sigma 3 being the components of the diagonal here. These three components are the principal stresses of the problem, and we also saw in the last lecture that we can calculate a variable or a stress known as tau max, the maximum shear stress, and this can be obtained if you know sigma 1 and sigma 3. So it's sigma 1 minus sigma 3 divided by 2, where sigma 1 is greater than sigma 2 is greater than sigma 3, and essentially what we have done is that we have ordered the principal stresses. So with that background, let us proceed further. So today we are going to define what is known as the Tresca stress, and Tresca stress can be calculated by using tau max here. So in the previous lecture we introduced tau max as sigma 1 minus sigma 3 by 2. So these are the maximum and minimum principal stresses respectively, and essentially tau Tresca is equal to tau max. So that's the definition of Tresca stress. Now of course you realize that we needed to calculate the principal stresses to get this value tau Tresca. Now the second stress we are going to use is the von Mises stress, and this is given by this slightly more cumbersome equation. So it is the square root of this entire quantity. So it's sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. This whole thing divided by 2, and then we take the square root of that. Once again, always remember that once we obtain the three eigenvalues of the stress matrix, sigma 1, sigma 2, sigma 3, we have to order them such that sigma 1 is greater than sigma 2 is greater than sigma 3. So now it's become clear to you that we essentially went all the way from the general stress matrix to the principal stresses to the tau Tresca and the sigma von Mises. So essentially the aim of this entire exercise was that at the end we could calculate these single variable or single stress conditions at a point, and this is because a single stress situation is much more easier to implement in terms of a failure theory. So what we were doing from a more philosophical perspective is going for a dimensionality reduction. So we reduce the dimensions from a 3 by 3 stress matrix to an eigenvalue based system, which is a diagonal stress matrix, and now we have obtained tau Tresca and sigma von Mises. So let us look at an example to clarify these somewhat abstruse concepts. So let us start with a simple stress matrix such as the one given here. So you can see here that sigma xx is 3, tau xy is 1, tau xz is 1, sigma yy is 0, tau yz is 2, and sigma zz is 0. And the stress matrix is of course symmetric, and all the stresses are given in terms of megapascal. Now we can very easily find the eigenvalue of this matrix. You can find this in MATLAB, you can find this using Python or any programming language or even a scientific calculator, or if you are somebody who likes to do this using determinants, you can do that also. And what you're going to get is sigma 1 is 4 MPa, sigma 2 is 1 MPa, and sigma 3 is minus 2 MPa. So like I mentioned before, the maximum stress is here, which is 4, and the minimum stress is here, which is minus 2 megapascal. So now we clearly know what is sigma 1, what is sigma 2, what is sigma 3. So we can immediately calculate tau max or tau Tresca as sigma 1 minus sigma 3 by 2. And so we get here 4 minus minus 2, and that becomes 6 by 2 or 3 megapascal. Now for the von Mises stress, the calculation is slightly more complex, but nothing too difficult, especially if you have a computer program. So you have to write sigma 1 minus sigma 2, which I've written here, 4 minus 1, sigma 2 minus sigma 3, which is 1 minus minus 2, and sigma 3 minus sigma 1, which is minus 2 minus 4. And then you do the necessary arithmetic here. You take the squares, you divide by 2, you take the root, and what we get is sigma von Mises is 5.196 megapascal. So let us now introduce Tresca failure theory, which is also known as the maximum shear stress failure theory. And this theory is valid for ductile materials, which we very frequently use in aerospace structures. So Tresca's failure theory says that failure in yielding occurs when tau Tresca equals Sy by 2 is sigma 1 minus sigma 3 by 2. So essentially what this means is that the Tresca stress is equal to Sy by 2, and we can immediately cancel the 2 here, and we can write this condition that Sy equals sigma 1 minus sigma 3 at the point where yield based failure takes place in the system or in the material. And of course here sigma 1 is greater than sigma 2 is greater than sigma 3, so it is assumed that you have ordered the principal stresses in this manner. Now Sy is the tensile yield strength, which is given to you for a material, which is typically calculated from experiments. So if you know Sy, you know sigma 1, you know sigma 3, you will know that at a given point has the material failed or not. Now let's look at the von Mises failure theory, which is also known as the maximum energy of distortion failure theory. And this also is valid for ductile materials. And here what this theory says is that failure and yield will occur when sigma von Mises equals Sy. So that's something you need to remember. Now remember, for sigma von Mises, there is this expression inside the square root and so on. So this expression was sigma von Mises, and so we have to equate this to Sy, where Sy is again the tensile yield strength. Once again remember that sigma 1 is greater than sigma 2 is greater than sigma 3. So we have arranged the principal stresses in this manner such that the maximum one is sigma 1 and the minimum one is sigma 3, and once we have these stresses we can very easily calculate the sigma von Mises here. Now I'll just do a simple example to illustrate the fact that the material fails or not largely depends on the failure theory you are using. So let us start with the sigma value given by this. So let's say this is the state of stress at a given point, and also we know that for this material Sy is 140 megapascal. Now for this particular matrix you can calculate the principal stresses, and they will be 100, 50 and minus 50. So these are the three principal stresses here, and in this case you clearly see sigma 1 is 100, that's the maximum, sigma 3 is minus 50, that's the minimum here. So we have ordered these principal stresses. Now I can immediately calculate tau Tresca as sigma 1 minus sigma 3 by 2. So that would be 100 plus 50 by 2, that would be 75 megapascal. And I can also calculate that Sy by 2 is 70 megapascal from the fact that Sy is 140 megapascal. Now I can take tau Tresca and I can see if at what point this equals Sy by 2, and that would be at 70 megapascal. At that point yield failure would take place. But for this given stress state, which is given by the sigma matrix here, tau Tresca is 75. So actually it is greater than the tau Tresca required for yield failure. So under this particular stress situation, that is 150 minus 50 diagonal stress matrix, the material would have failed at this test stress state because tau Tresca is higher than Sy by 2. So that's something which Tresca failure criteria at least predicts for this particular stress state. Now let's take the same stress state and now let's apply the von Mises failure criteria to it. So again the eigenvalues remain same because the matrix is same. So it's sigma 1 is 100, sigma 2 is 50, sigma 3 is minus 50 megapascal and Sy is 140 megapascal. Now I calculate sigma von Mises, so this is somewhat more complicated calculation, but I know for example sigma 1 is 100, sigma 2 is 50, sigma 2 is 50, sigma 3 is minus 50, sigma 3 is minus 50 and sigma 1 is 100. I do this calculation in a calculator and I get sigma von Mises is 132.29 megapascal. Now you can see that failure would take place based on the von Mises criteria when sigma von Mises equals Sy equals 140 megapascal. That's the requirement for yield failure. But in this case what has happened is that sigma von Mises is actually 132.29 megapascal. So it is lower than Sy. So that means according to the von Mises failure criteria, this material will not fail at this stress state. So this example I have created to show to you that in this particular case, while Tresca theory shows that the material will fail, von Mises theory shows that the material will not fail. So whether a material fails or not also depends on the failure criteria you are using for that particular problem. So what can we say about these two failure criteria which are widely used in the design of various structures? We can certainly see that Tresca failure criteria tends to be more conservative than the von Mises failure criteria, and it can often tell the material has failed at a lower stress point than the von Mises failure criteria will tell you. Now, in many cases, it has been proposed that the von Mises failure criteria is more accurate, and one of the things, of course, you can think about is that as far as aerospace structures are concerned, because weight is something which you always want to keep as low as possible, it may be better to go with a less conservative failure criteria, which would be the von Mises failure criteria here. But do remember that there are various rules and regulations, there are various established practices in different companies and by different certification bodies and so on. So you need to keep all those things in mind before you choose a particular failure criteria. Now from the theoretical perspective, we clearly see that principal stresses were key to the failure criteria. So whether we talk about tau Tresca or whether we talk of sigma von Mises, both these depend on sigma 1, sigma 2 and sigma 3. In fact, tau Tresca only depends on sigma 1 and sigma 3, but sigma von Mises depends on all these three principal stresses. So today's lecture is very important because it informs to you that there are these various failure criteria out there, and this is one of the reasons why we spend so much time studying principal stresses and so on. So very often when students are introduced to this concept of principal stress, especially in many books, they don't talk about it simply in terms of the eigenvalue of the matrix. They talk about various transformations and so on and derive various cumbersome formulas, but you can actually do it in a more simpler way by thinking of it in terms of matrices. But all this effort is because the failure criteria are expressed in terms of principal stresses. Principal stresses have done a dimensionality reduction of the stress matrix, and then a further reduction is done using the failure criteria, and that's something which is very important because you will see many a time that any aircraft, any gas turbine, any steam turbine, anything you are designing in a structural system, maybe it's even a bridge, what you are going to do is that you are going to plot the various stresses which act on this entire body. So there are softwares which are going to give you the Tresca stress, there are softwares which are going to give you the von Mises stress which acts on the complete body, and they are even going to color code this particular stress depending on where the stress is high, where the stress is low and so on. So maybe it's going to give you a red color where the stresses are very high, and you need to make sure that nowhere on the aircraft structure is there failure taking place. So that is something very important for engineers to ensure because do remember that failure is something which we do not want to have in any aircraft structure, because people are involved and lives are involved. And so it's very important for the aerospace engineer to make a good trade-off between trying to keep the costs and weight as low as possible while ensuring that the safety and security of the aircraft structure is maintained. So I'll stop this video now and I will see you in my next video. See you then.